The bulk of the material that we're going to see on tomorrow's test deals with systems of equations and systems of inequalities. When we're talking about systems of equations, we've only talked about one method for solving them up to this point, and that's to find their intersection. So we're graphing to find an ordered pair that satisfies both of these equations. So if I take the first equation and in our graphing calculator we enter that into y1, y equals 3x plus 1. And we take the second equation, y equals 3x minus 4, and we enter that in y2. And then we graph those two equations. It's going to look something like this. So if I sketch this graph, and that's all it asks us to do in the instructions on our coordinate plane over here, our graphs would look something like this. It doesn't have to be pretty. Alright, what we need to know again is that if our lines cross in one place, that place where they cross, where they intersect, the ordered pair, the coordinates of that point is going to be the solution. So since these two lines appear to be parallel lines, they have the same slopes, they're never going to cross. And if they never cross, that means that they have no solutions. So that would be our answer to number 1. No solutions to that system of equations. Looking at number 2, well, these two we would have to solve for y before we can enter in the calculator. So I'm going to take that first equation, 3y plus 15 equals 6x, and get rid of everything on the left-hand side of the equal sign except for y. So I'm going to subtract 15 from the left and from the right so that the 15's cancel. And once we've done that, what we're going to be left with is 3y equals 6x minus 15. At that point, we're one step away from having y by itself. We need to divide the left by 3 and divide the right by 3 so that the 3's will divide to give us 1. So 1y, or just y. So y equals 2x minus 5 after we divide. So once we've gotten that equation solved for y, we're ready to enter that in y1. Then we need to take our second equation and solve it for y as well. So that's going to look like this. 2y plus 4x equals 18. We need to get rid of the 4x on the left by subtracting it to make these terms add together to equal 0. So 4x minus 4x is going to give us 0, leaving us with only 2y on the left. It's going to leave us with negative 4x plus 18 on the right. From that point, we'll divide the left and the right by 2 so that the 2's will divide to give us 1, leaving us with y equals negative 2x plus 9. At that point, that equation is solved for y, which means that we're ready to enter it into y2. So I'm going to take the calculator then and hit the y equals button and enter these two equations. Y equals 2x minus 5 and y equals negative 2x plus 9. When we hit graph, we're going to see that as opposed to number 1, this system of equations does intersect at a single point. So if we look on our calculator and we see one intersection, that means that we are going to have one solution, because there is one point that those two lines have in common. So I'm going to graph those two lines over here on the coordinate plane. Again, they don't have to be gorgeous. We're going to use the calculator to help us find the exact intersection, so we don't need to draw this perfectly by hand. There is a process that we said we can take to let the calculator find the coordinates of the intersection for us, and that is to hit second trace and then choose number 5 where it says intersect. It says first curve, well, we're on the first line, so hit enter. Second curve, we're on the second line, so hit enter. And then guess, I'm just going to get somewhere, scroll over somewhere close to where it looks like they intersect. Doesn't have to be exact, and hit enter again. When we do that, it gives us the coordinates 3.5, 2. So these are the coordinates of a point that would satisfy both of these equations, to where if we plugged this value in for x and this value in for y, it would make the left-hand side of the equation equal to the right-hand side of the equation. So again, on number 2, since these two lines crossed at a single point, we had a single ordered pair. That was our solution to that equation. Looking at number 3, we have another system of equations where we'll need to solve for y before we can graph them. So taking the first equation, x minus 2y equals 6x, we would first subtract x from the left and then from the right. So the x's on the left are going to subtract to give us 0, leaving us with negative 2y equals 6x minus x. Well, these happen to be like terms, so we can subtract them. 6x minus x is 5x. At that point, we're one step away from having y by itself. We'll divide the left by negative 2 and the right by negative 2. That's going to leave us with y equals negative 5 halves x. And that is implied, for the purposes of graphing, negative 5 halves x plus 0. So the y-intercept is going to be 0 if we needed to graph that by hand. But again, if we're using our calculator, then we can just leave the plus 0 off. At that point, this equation is ready to be entered in y1. Our second equation, we just need to take one step to get y by itself. We need to divide both sides by 4. So 4 divided by 4 divides to give us 1. So y equals 2x divided by 4. Well, 2 4s reduces to 1/2, so 1/2 x. 12 divided by 4 is 3, so minus 3. And at this point, our second equation is ready to be entered into y2 in our calculator. Again, it doesn't matter really which one we enter in y1 and which one we enter in y2. So we're going to enter negative 5 halves x plus 0, or we can just leave that off, and then 1/2 x minus 3. If we hit graph, we're going to see that those two lines cross in one point. That, again, on number 3, that means that this system of equations has one solution, and then it tells us in the instructions to identify what the solution is. So our solution is going to be the point where they intersect. So we'll push second trace and choose number 5 that says intersect. Hit enter for the first curve, hit enter for the second curve, and guess, hit enter one more time, and it's going to give us our ordered pair of 1, negative 2.5. So those are the coordinates of the point where those two lines intersect, which means that it's a point that's on both of the lines, so it's a solution to both of the equations. So that's how we solve systems of equations by graphing. Numbers 4 through 6 are a little bit different, because now instead of systems of equations, we're looking at systems of inequalities. And the only thing that's going to be a little bit different about this is the way that our solution is going to look. Our solution for systems of equations were a single ordered pair where the lines intersected. Our solution for systems of inequalities is going to be the shaded region, it's going to be the intersection of the shaded regions of these two inequalities. So we need to graph these two lines just like we would if they were equations, starting with the y-intercept of negative 1. And then counting slope. Our slope is negative x, or negative 1x, which is the same thing as negative 1 over 1. So from our y-intercept, we'll count up 1 and left 1 to give us a negative slope through those 2 points, or down 1 and right 1. Once we've gotten 2 or 3 points on the line, we're ready to draw the line through those points. And the type of line, again, depends on what type of inequality symbol we have in this problem. Since we have a line underneath the inequality symbol, that tells us that we want to have a solid line. So we're going to draw a solid line that extends through those 3 points that we just graphed. So it'll look like that. Then we know with an inequality, we're not just going to draw a line, we're going to shade a region of the graph. And in this case, since it says y is greater than or equal to negative x minus 1, we're going to shade all of the points that are above that line. Again, if it says greater than, we're going to shade above. If it says less than, we're going to shade below. So this purple region on the graph is not the answer to our system of equations. This is just the region that would make the top inequality true, the region of ordered pairs. So any point that lies in this shaded region in the purple would make the top inequality true. Then we need to graph the bottom inequality. The bottom inequality has a y-intercept of positive 1, so we'll go up to 1 on the y-axis and put a dot, and from that point we'll count slope, and our slope is 2 over 1. So we'll go up to right 1 in a positive direction, up to right 1, or we could go down to left 1, down 2, left 1, and we're going to see that that forms a straight line. Since our inequality symbol is less than or equal to, that means that the line itself is included in our solution set. Then we want to draw a line that is, again, solid. So we'll draw a line that looks like this, and once we've drawn that line, then we need to shade the region that it tells us to on our second inequality. Since it says y is less than or equal to, then that tells us we're going to shade below the line we just graphed, so it'll look like this. Shade everything, again, below that second line that we just graphed. So what we're looking for, again, are the ordered pairs, or the region of the coordinate plane that contains the ordered pairs of all of the points that would make both inequalities true. So once we've made our graph, we're going to see 4 distinct regions of our coordinate plane. There's the region over here in white. It hasn't been highlighted in purple or yellow. That would be the region of coordinates or ordered pairs that doesn't satisfy either inequality. The purple region at the top would satisfy the top inequality, but not the bottom inequality. The bottom section that's just in yellow would satisfy the bottom inequality, but not the top one. And then we have a shaded region over here to the right where the purple and yellow regions overlap. These would be all of the ordered pairs that would satisfy both inequalities. So this would be our solution set. This region would be. So a way that you might be asked this type of problem on a test is it may give you 4 ordered pairs and it say which of the following is a solution to this system of equations, and we would find the ordered pairs that are in that overlapping section and find the ordered pairs that are not in that overlapping section. For instance, if I find -3, 2, -1, -2, -3, it's located right here. It's not in the shaded region, which means that that is not a solution to the system of inequalities. If I find 4, 2, 1, 2, 3, 4, up 2, this is in the overlapping section of that graph, which means that that is a solution to the system of inequalities, meaning it would make both of the inequalities true if we substituted the ordered pairs x and y values in. Looking at number 5, we're going to do the same thing where we want to graph both of these inequalities on the same coordinate plane, which first requires us to solve each inequality for y. We want to get y by itself. So x minus 2y is less than 0. We want to subtract x from the left and from the right so that the x will subtract to give us 0. That's going to leave us with negative 2y on the left-hand side of the inequality. On the right-hand side, negative x plus 0, or we can really just write that as negative x. At that point, we're one step away from having y by itself. We need to divide the left by negative 2 and divide the right by negative 2. The negative 2's are going to divide to give us positive 1, which just leaves us with y. On the right-hand side, negative x divided by negative 2, that's just the same as negative 1x. Negative 1 divided by negative 2 is positive 1/2, so 1/2 x. Since we divide by a negative 2, we need to flip our inequality symbol from less than to greater than. Once we've gotten that done, once y is by itself, we're ready to graph that inequality. We know that this line is going to cross the y-axis at 0. Remember, we could add just plus 0 out there to the right-hand side if we needed to. So I'm going to put a dot on the y-axis, really just at the origin at 0. From that point, we're going to count slope of 1/2, so up 1 and 2 to the right, or we could go down 1 and 2 to the left to get that positive slope. Then we're going to draw a line that extends through those points, and since our inequality symbol just says greater than, we're going to draw a dotted line through those points. So this would be the graph of that line. Then we need to shade the region that's represented by this this inequality, and since it says y is greater than 1/2 x plus 0, we know that we're going to shade above that line that we just graphed. So all of the ordered pairs that fall in this purple shaded region would make the top inequality true. Well, if this is a system of inequalities, again, just like on number 4, we need to know not just the the area of the coordinate plane that makes the first inequality true, we need to see the overlapping section of the two shaded regions, because that would be the region that makes both of the inequalities true. Then we're going to take our second inequality in this problem and solve it for y over here. So 2x plus 3y is less than or equal to 6, so we need to subtract the 2x from both sides. And once we've done that, we're going to end up with 3y is less than or equal to negative 2x plus 6, and then divide the left by 3 and both terms on the right by 3. So the 3's divide to give us 1, so we end up with 1y or just y. So y is less than or equal to negative 2/3 x plus 2. So this inequality tells us that we have a y-intercept of positive 2, so we'll plot that point, and then we'll count the slope from that point to find some other points that happen to fall on that same line. So our slope is negative 2/3, so we could go up 2 and 3 to the left to get a negative slope, or we could go down 2 and 3 to the right to give us a negative slope. Once we've done that, we're going to see a line that would angle, and it would intersect our other point, or our other line, and we are going to draw, in this case, a solid line, since it says less than or equal to. So our line would look like that, and then we're going to shade a region of the graph, and the region that we're going to shade is below that solid line that we just graphed, since it says less than or equal to. Once we've done that, we're going to see, again, 4 sections of this graph that look all a little bit different. There's a region that's in white. The white region to the right-hand side would not, those coordinates, those ordered pairs would not make either of the inequalities true. The purple shaded region at the top would only make the first inequality true. The yellow region to the bottom would only make the second inequality true, but this region over here to the left-hand side would make both inequalities true. So just to emphasize again what our solution set actually is, it's not like this is kind of the solution, this is kind of the solution, and this is the solution. This is the only part of the graph that represents our solution set. So just to emphasize that, I'm going to erase everything that's below these two lines, and this might mess us up a little bit, but I just don't want for anybody to have any misconceptions here. So this is not part of our solution set, and this purple part up at the top is not part of our solution set either. Only the part that is over there to the left-hand side that has the purple and yellow overlapping. So this would be the solution set. So again, any ordered pair that's over here in this shaded region where the purple and yellow overlap is part of the solution. Any ordered pair that is outside of that region is not a solution. So looking at number 6, same type, we need to solve both of those equations for y. So we need to say minus x minus x. So once we've done that, we're going to have y is greater than negative x plus 5. That means we have a y-intercept of positive 5, so we'll put a dot there. And then we have a slope of negative 1, which means up 1 and left 1, or we'll have down 1 and right 1. So then we'll shade with a dotted line through, or we'll draw a dotted line through those points. Again, it's a dotted line because of the inequality symbol. It just says greater than, it doesn't say greater than or equal to. And from that point we need to shade, and we're going to shade, in this case, since it says greater than, we're going to shade above that dotted line to where it looks like this. Then we'll graph our second inequality. Our second inequality needs to be solved for y also, so we'll subtract x from the left and from the right so that the x's subtract to give us 0, leaving us with just y is less than or equal to negative x plus 1. Well, just before we graph this, let's notice something about these two inequalities. We had a slope of negative 1 and a slope of negative 1. That means we're either going to have parallel lines or the exact same line. In this case, we have different y-intercepts. That means we're going to have different lines, but they're parallel. So our y-intercept of our second line is going to be at positive 1, and then from that point we're going to count the slope of negative 1, which is up 1 and left 1, or down 1 and right 1. Since this says less than or equal to, we're going to draw a solid line that extends through those points. That looks something, well, that's a solid line, a dotted line. Again, we need a solid line. So it's going to look something like that. Once we get that line graphed, then we're going to shade everything in this case that falls below that line we just graphed. So it's going to be the yellow region down here. So once we've shaded those two regions, we're going to see that these two shaded regions don't overlap at all. If those two shaded regions don't overlap at all, then we would say that there is no solution. Again, the reason that there is no solution is because there is not a single point in existence that that would satisfy both inequalities. There's a purple shaded region up here and then a yellow shaded region down here. They never cross, they never intersect, which means that they have no points in common. I hope y'all found this helpful. I'll continue with number 7 in part 2 of this video.